the non-gravitational acceleration of the interstellar object 3I/Atlas, which has been monitored and routinely updated by Davide Farnokia through NASA's JPL Horizon system, has undergone a series of surprising and rapid revisions that raise significant questions about the physical behavior of the object and the models used to track its trajectory. On October 30th, 2025, JPL Horizons listed the radial non-gravitational acceleration coefficient A1, normalized to 1 astronomical unit, as 1.6 times 100/day superscript 2. This magnitude suggested a relatively strong non-gravitational influence, consistent with outgassing processes traditionally associated with sublimation of volatile materials as an object approaches the Sun. Yet by November 24th, that same coefficient had been reduced by a factor of 4 to 4 times 100/day superscript 2, indicating either a sudden reinterpretation of observational data, an improved fit to newly collected measurements, or a recognition that the previous model overestimated the object's radial acceleration. Around that same time, I drew attention to a remarkable and statistically unlikely coincidence: the forecasted Parahove distance, meaning the closest approach of 3I/Atlas to Jupiter during its encounter on March 16, 2026, was predicted to be 53,445 plus or minus 0.06 million kilometers. This distance is essentially identical, within 1 standard deviation, to Jupiter's Hill radius at the time of the encounter, calculated to be approximately 53,502 million kilometers. The Hill radius marks the region within which Jupiter's gravitational influence dominates over the tidal pull of the Sun. Objects passing slightly within this radius may be captured, at least temporarily, by Jupiter's gravitational sphere of influence, while those passing even modestly outside it cannot remain bound and will be stripped away. The idea that an interstellar object, one with no prior dynamical relationship to Jupiter, would approach at a distance matching the Hill radius so precisely is extraordinary, and such a close alignment raised immediate questions about the physical modeling and the potential significance of this encounter. Intrigued by this improbable match, I contacted Davide Farnokia and shared my analysis, pointing out that the Parahove distance and the Hill radius were aligned to an extent that seemed far too precise to be dismissed as numerical coincidence. Despite sending my detailed report, I received no reply. Yet, within only a few days, the A1 value listed on JPL Horizons was updated once again, this time revised downward by an even larger factor of 6, reaching a new value of 6.8 times 100/day superscript 2. Along with this change, the Horizon software adopted an entirely new functional model for the radial dependence of the non-gravitational acceleration acting on 3I/Atlas. Instead of using the steeper Marsden-type water ice sublimation curve that had long served as the standard for comet tracking in the inner solar system, the system transitioned to an inverse square, 1/r superscript 2, dependence more appropriate for carbon dioxide, CO2, sublimation. This shift is notable because CO2 sublimates efficiently at distances interior to roughly 5.0, whereas water ice sublimation follows a much steeper radial dependence and becomes significant only at smaller heliocentric distances. The revision suggests that JPL Horizons implicitly reinterpreted the physical nature of the outgassing activity driving the observed non-gravitational acceleration, proposing that CO2 sublimation, rather than H2O sublimation, better fits the available data for 3I/Atlas. While such a change might be justifiable physically in cases where CO2 is known to dominate, the timing of the switch, coming immediately after attention was drawn to the Parahove Hill radius coincidence, makes the revision appear reactive rather than purely data-driven. Using this updated, shallower radial model, JPL Horizons recalculated the trajectory of 3I/Atlas and produced a new Parahove estimate of 53,587 plus or minus 0.045 million kilometers. Unlike the earlier forecast, this new value now places the closest approach distance slightly outside Jupiter's Hill radius at the relevant epoch. In practical terms, the updated trajectory removes the earlier possibility that 3I/Atlas might cross into Jupiter's gravitational capture zone, thereby eliminating the striking coincidence that had initially drawn attention. However, this new result rests heavily on the assumption that the 1/R superscript 2 CO2-driven non-gravitational model accurately describes the physical processes acting on 3I/Atlas throughout its orbit. This assumption is highly questionable. Observational evidence indicates that the object brightened significantly more than expected as it approached perihelion, suggesting enhanced activity that departs from the smooth profile predicted by a simple 1/R superscript 2 model. Peaks in brightness imply episodic or sharply increasing outgassing, which would require a steeper radial dependence, more like the water ice sublimation function used in the earlier Marsden model, or possibly an even more complex function accounting for delayed activation, thermal lag, or heterogeneous surface composition. A model that oversmooths these processes inevitably misallocates the magnitude and timing of the non-gravitational force contributions, especially those occurring near perihelion, where activity is strongest. If the true radial dependence of the object's outgassing is steeper than the adopted CO2-based model, then the inward acceleration near perihelion is being underestimated, while the influence from larger distances is being overestimated. This mischaracterization shifts the inferred starting conditions used for orbit propagation and therefore biases the predicted future trajectory. As a result, the recalculated Parahove distance, slightly outside the Hill radius, may be artificially inflated. A corrected model, one that properly accounts for the enhanced perihelion-driven acceleration, would likely redistribute the non-gravitational contributions, reducing the importance of distant, low-activity phases and increasing the weight of the high-activity perihelion interval. This rebalancing would pull the predicted Jupiter encounter distance back inward, restoring the earlier match to the Hill radius and potentially strengthening the case that the initial forecast was closer to the truth. Because 3I/Atlas is an interstellar object, its precise dynamical evolution carries broader implications. Unlike long-period comets that may have interacted with the outer solar system multiple times, interstellar visitors are sensitive to non-gravitational modeling because such effects accumulate over long, unbound trajectories. A small misestimation in A1 or its radial dependence produces a disproportionately large error when propagating the orbit years into the future or past. In addition, because interstellar objects are expected to show unusual compositions, surface structures, or sublimation behaviors, applying a standard cometary model, whether H2O-based or CO2-based, is inherently risky. For these reasons, abrupt model changes dramatically affect trajectory predictions, and such changes must be justified through transparent reasoning and observational evidence, rather than adopted merely for numerical convenience. Taken together, the rapid sequence of revisions, the 4-fold reduction in A1 by late November, the 6-fold reduction shortly thereafter, and the shift to a different physical model, suggests not only that the observations are challenging to fit, but also that the underlying physical assumptions remain unsettled. When multiple major parameter adjustments occur in such a short period, especially around the time that an anomalous dynamical coincidence is pointed out, it becomes reasonable to suspect that the existing models are inadequate to capture the true behavior of the object. The concordance between the earlier predicted Parahove distance and Jupiter's Hill radius may not have been a coincidence at all. Instead, it may reflect the true dynamical path of 3I/Atlas, one that the updated but oversimplified model is now obscuring.